Let's move on to production technology. Okay, so image of the smaller structures. So modern technology requires efficient electronics in the smallest spaces. Thanks to optical technologies, it is possible to organize increasingly smaller electronic components on semiconductor chips. So you can see here in time, and this is the structure, the size of the structure. So in 1970s, the size of structures or chips or components used to be about 10 micron. So over the year, they started to reduce 6 micron, 3 micron, 1.5 micron, and now in 2020 we are talking about 5 nanometer chips. All right, very, very small. So the image of increasing smaller structures require light sources with very short wavelengths. So in order to make these very small chips, we need what we call an extreme ultraviolet, or we call it EUV light. It is already in use and its wavelength is only 13.5 nanometers, and it requires the application of purely reflective optics with extremely accurate geometry. So you have the beam source, the extreme ultraviolet light, so it's reflected by different mirrors, and then it obtains the mask from the photomask over here, and finally it's reflected and then it is embedded on the wafer. This is the chip. Okay, so the image that is taken from the photomask is transferred to the wafer. So this is what we call extreme ultraviolet lithography. Precise laser drilling. So ultra short pulse lasers drill differently sized, accurately shaped injection nozzles that distribute the fuel in the best way possible. So thanks to laser precision machining, up to 30% of fuel can be saved. Okay, so you have a laser pulse which can produce, pulse, right? On off pulse. So up to 800,000 pulses per second, and the lens focuses the pulse laser beam on a 10 micrometer diameter. So this diameter is 10 micrometer, very small. So the heating of adjoining material is avoided by laser pulses shorter than 10 picoseconds. So since the laser pulse is very small, the nearby material is not heated up and doesn't break away. So you can make very, very precise nozzles. So these nozzles are used in the engine. Okay, you have the spark plug over here, and you have different injection nozzles, different sizes. You have the fuel coming out, and this is the cylinder and the piston over here. So you can see enlarge of the injection nozzle, so different sizes. So all these were created using a laser pulse. Okay, ultra short pulse laser. So very precise, and you can control the diameter and the size of the nozzle. Laser cutting. Laser cutting enables very quick processing of materials with a low loss of material, which makes this method extremely energy efficient. So you have efficiency and performance comparison of conventional milling and also laser cutting. So this shows a cutting of a 5 mm thick steel plate for 1 meter using conventional milling technique and also the laser. So let's compare in terms of the cutting width. Okay, the width, lebar. So if you're using the conventional milling, which is in green, the width is very huge, 10 mm. But if you're using a laser, you can see the width is very small, only 0.4. The tool performance, all right, the conventional milling, the performance is very low, 0.4, a lot of loss, whereas the laser, the performance is about 20 kilowatt, very high performance. The duration per meter, the conventional milling needs 14 minutes to create a 1 meter cut, whereas the laser only requires 12 seconds, very fast. Energy consumption in terms of kilowatt hours, conventional milling 0.1, and laser very, very small, 0.07 kilowatt hours only. In terms of waste, how much of material is wasted? The conventional milling will waste almost 390 grams of waste, and laser will only waste 15 grams of waste. In terms of total energy consumption, taking into account material savings, conventional milling gives us 2.05 total energy consumption, and laser, of course, very conservative about energy consumption, is only 0.14. Smartphones, thanks to the laser. So hundreds of thousands of smartphones are manufactured daily, and the quality and efficiency of production are of crucial importance to the manufacturers in this competitive market. So lasers are the key to success here. So as you can see here, many different laser types are used to manufacture a smartphone. You have the fiber laser, you have the ultraviolet solid state laser, carbon dioxide laser, ultra short pulse laser, ultraviolet excimer laser, and infrared diode laser. So these lasers are used to make different machine processes, for example, to make an edge, to make a pattern, to make an area, and also to make holes or vias. Okay, let's look at the touch screen. This is the outermost layer of your smartphone. You can see two different lasers are used here. The first is for the cutting of extremely thin hardcover glass, the hardcover glass that you can see here. So you use an ultra short pulse laser. The cutting of the touch screen foil, you have your touch screen foil, it is also done with ultra short pulse laser. Structuring of the conductive layers, okay, beneath this touch screen there is a conductive layer, and it is done or structured by a solid state laser. You have your screen, the next layer. So there is existence of a polycrystalline layer in the screen layer. So the generation of this polycrystalline layer is done using fiber lasers, and the encapsulation of the laminated glass is using IR diode laser. The battery, so the welding of the battery case is done using solid state laser. The marking of the logo, the data matrix code, and the serial number is done using a carbon dioxide laser. Okay, so it's an area. Okay, and then moving on, you have the circuit board. The structuring of the conductor tracks, the cutting of the foil circuit boards, the drilling of the contact holes are mainly done using UV solid state laser and also solid state laser. And last but not least, the housing, the cutting of the housing and the marking of the logo and also the serial number, they are executed using fiber lasers and also CO2 lasers. Okay, so different lasers for different parts of your smartphone. 3D printing. So based on a computer drawing, complex structures can be produced from plastics, ceramics, and metals with the help of selective laser melting. So dentures, gigi palsu, dentures and implants are among the rapidly growing number of applications. So you have the general operating principle. The digital model of an object is transformed into a model made of a series of thin layers. So first of all, a layer of powder is applied. The powder melts in the component's cross-section according to the specifications of the layer model, and then the build platform is lowered with every layer. So you start to lower the layer. So what happens is the application, the melting and the lowering repeats itself until the object is finished. So you put one layer, then the laser melts it, and then you go to the next layer, and so forth. So you have a series of layers. At the end, the material that has not melted will be removed. The actual object is then left. So what was initially projected will be made using the 3D printing. Okay, we move on to data transfer. Okay, so we move on to optical fiber networks. So in 1988, the first transatlantic optical fiber cable, the TAD-8, went into operation. So optical fiber quickly replaced copper cables to meet the fast-growing need for greater capacity. Today, submarine cables with capacities of up to several terabytes per second connect the whole Earth. So optical fibers offer substantially higher transmission rates while simultaneously providing large ranges. Other advantages are lighter cables, lower space requirements, and fewer repeaters. The operation and maintenance costs are also significantly reduced. So here is a comparison between an optical fiber cable and also a copper cable. So in terms of the diameter, you can see that the optical fiber cable is 10 micrometers thick, and the cladding is about 0.6 millimeters. In comparison, the cross section in original size for the copper cable is 1.1 millimeter, and the cladding is 6.9 millimeters. So copper cables are generally larger than the optical fiber cable. So now let's look at transfer speed. For optical fiber cable is 1000 megabits per second, about 1 gig. But for copper cable is only 50 megabit per second, so it's lower transfer speed. In terms of range, optical fiber cables can go up to 100 kilometers without any amplifier or repeater. But a copper cable, for every 2 kilometers, an amplifier or a repeater needs to be placed. The shelf life, how long can an optical fiber cable last? It can last for 50 years, whereas a copper cable can only last for 5 years. In terms of weight, the fiber cable is very light. 100 meters of cable in kg is only 0.6 kg. This is 100 meters of cable versus copper cable, since it's made from metal, it's 5.8 kg. 100 meters is 5.8, so very heavy. Energy consumption in watts per user, optical fiber cable only consumes 2 watts, very low power consumption, versus versus copper cable, it requires 10 watts per user, so higher energy consumption. So definitely optical fiber cable is the choice for transatlantic optical communication between countries. Okay, let's look at the laser communication in space. So free space optical communication between near Earth and also geostationary satellites enables the fast transfer of data to a ground station. So vital data during natural catastrophes, suppose there's an earthquake or a flood, okay, some catastrophe, major catastrophe, okay, and or in emergencies at sea, can be received almost in real time in this way. Okay, so the advantages of laser is very clear cut: large data volumes, there is no limit, there is no frequency of allocation, lower energy consumption, therefore it expands shelf life, and it's very light, less mass, and therefore it saves cost. Okay, so the laser and the optics, they meet the highest requirements. They have the smallest tolerance for generating a bundle laser beam across large distances. So the beam size is very small and it can travel hundreds and hundreds of kilometers, and it is very stable despite great temperature differences. So it is stable in cold weather or hot weather, and it can survive strong vibrations and accelerations during rocket launches. Okay, and it is over 15 years maintenance free. The shelf life is very high. It is also resistant against ultraviolet and gamma radiation in space. So as you can see here, the near Earth satellite, it scans parts of the Earth's surface, and it sends through a satellite laser link, it sends it to the geostationary satellite over here. So what happens is this satellite then transmit the information back to a receiving station which is on Earth. So suppose this area there's a flood or there's an earthquake, so this information is sent here and then it's sent back to the receiving station, and then it will be communicated to humans to say that an earthquake is happening here, an earthquake or a tsunami or whatever. Okay, QR codes. So cameras and optical sensors often work together with intelligent image or data processing. So the QR code, its QR short form is quick response. It shows this impressively. So QR codes are actually two-dimensional barcodes. A camera phone with appropriate code reader software recognizes this information and decodes it. So this is what a QR code looks like. So you scan the QR code with your camera, and then it decodes it, and then you can access to a particular website. So the QR code structure, apart from the content, it contains several elements. so that the software can recognize the data accurately. So there's a position and data, there is a format, the one in light green is the format, timing, how long does it take to access that particular website, the version, and also the alignment. So there are up to 4,000 alphanumerical characters which are fit into a QR code. So in comparison to the classic barcode, QR codes can store more information on a smaller area, and it can make fewer requirements of reading devices. They also function even if they are partly damaged or corrupted. So you can put in more information in a QR code compared to a normal barcode. And then you see, even if it's distorted or it's blurred or it's twisted, you still can get the information that you require. So this is done using a laser and a receiver. Okay. Let's move on to image capture and display. Okay. So this is a comparison of camera lenses. So today, brilliant images are possible with the smallest smartphone lenses. So why then is it still necessary to have large lenses in photography? So this is your smartphone lens, the camera inside your smartphone. And this is what we call an SLR lens, for people who use photography, SLR lens. So look at the comparison. So this is so small and this is so huge. And in terms of the lens arrangement, so despite their small size, smartphone lenses have sophisticated optics with complex lens arrangement. Okay, so there are many different types of lens in a smartphone, and of course in an SLR there are more complex lens arrangement. So the most important consequence of the size difference is the different depths of field. So in a smartphone lens, it can display all objects from near to far with the same sharpness. But in an SLR lens, the depth of field can be set selectively with large SLR lenses. Suppose you want to focus on this person, you can zoom, and using an SLR, you can just focus on this person. So it can be done with a normal smartphone. Gesture control. Optical systems, they can capture and interpret hand movements contactlessly. So this is ideal in a sterile workplace such as a hospital operating room. So this doctor, he needs to go in for surgery. So therefore he needs to make sure that his hand is sterile. He cannot touch any doors. He cannot touch anything before he performs the surgery. But how does he get into the surgery room? So we have this surgical hand tracking system. So basically it comprises of a line laser, and also there is an IR lighting as well as IR camera, light source, and also a 3D camera. So you have two infrared cameras, we call it IR camera. They capture the scene like two human eyes from slightly shifted perspectives, and then a 3D camera which is based on the propagation time of light verifies the distance. So you have a 3D camera over here. So the IR camera captures the image. So the 3D camera measures the distance. The system captures the finger position of the doctor, and the line laser marks the interactive area. So he shows his finger and then it tracks it, and then you have a match and the door opens for the doctor to go in. Okay. Flat screens. In contrast to early cathode ray tubes, flat screens have saved a great deal of energy per unit area. So the impressive global production capacities meet the high demand for these displays. So let's compare the electricity consumption at a same display size. So this is a cathode ray tube, the TV those days, but nowadays it is replaced with liquid crystal display, LCD. So the electricity consumption is 100% in a cathode ray tube versus in an LCD is only 25%. Production of flat screens within 1 hour. So in 1 hour, we can make 200,000 smartphone displays. And in 1 hour, the total area of produced flat screens, which includes TVs, tablets, smartphones, and others, is equivalent to 2 football fields. Okay, so that is how many flat screens that can be made. So many, alright, compared to a cathode ray tube. Now let's compare an LCD versus OLED. So LCD, which stands for liquid crystal display, it dominates the flat screen market, but in smartphones, organic LED, or we call it OLEDs, are conquering an increasingly larger market share. So OLED displays are thinner, they are more energy efficient, and they are higher in contrast, but they are more expensive to produce. Now let's compare the LCD display structure with the OLED display structure. So basically today's most common type of display creates images by blocking off or letting through white light that LEDs create across the back of the display. So you have the background lighting and it travels through until the front until the cover glass. So in between you have glass filter with polarizing films, you have color filters, you have liquid crystals, and also you have thin film transistors. And there is also LED strips to provide the background lighting. Okay, whereas in OLED display structure, we have organically luminous materials in OLED. It displays and it do not require a separate light source, which makes their construction depth much thinner. So you have a carrier plastic or a glass or a plastic, and then you have a thin film transistor, and then an anode. You have organic layers, so the molecules are electrically excited to make them glow, cathode, and also the cover glass. So light which is emitted from here, you can be seen here in the cover glass. So these layers are 200 times thinner than a human hair, very very thin for the OLED TV screen. And this shows the display resolutions in pixels. The standard resolution, normally if you're buying a TV, they will ask you what kind of resolution you're looking for. So the standard resolution is 720 times 480 pixels. Full high density 1920 times 1080. 4K ultra high density and 8K ultra high density. This simply means there are more lasers and detectors, LEDs and detectors to show you the picture. Alright, so that's what's the meaning of pixels. Medical technology, photonics in medical technology. Okay, seeing near and far. Individually adjusted varifocals help older people have good vision for all distances. A variety of criteria is included in the calculation for personalized and individual lens design. CNC machines are used to translate the calculated design into individual lenses with micrometer precision. So you have someone who needs specs, so they need a spectacle adjustment, they need the various characteristics. Suppose he's a runner or he's just for office wear, and then the eye and head movement, fitting height, and all these different criteria. So the lenses can be used for different types of eye correction, myopia or hieropia, and then it can be astigmatism, and then the axial distance, the prismatic, which is associated with heterophoria. So different types of eye correction. So you have computer calculated lens design based on the eye correction and also based on the person. So the different colors indicate the varying refractive power of the lens, from red, so this is high refractive index, to blue, low refractive index material. And we can create this varifocal. So you can see here, this is for near vision, that means to read and so forth, medium vision, and this is for far, while driving and so forth. So the whole thing can be constructed using a laser. Seeing clearly again. So from the age of 60 onwards, most people get a slight cataract. We know it's also known as a grey star. So treating cataracts is the most common operation around the world. Okay, and the WHO estimates that by 2020 32 million cataract operations will be performed. So we use the femtosecond laser with ultra short pulses, which allows a precise and careful operation. Remember the Nobel Prize, which was won in 2018 by the team. So it is used for medical technology such as in LASIK. So this is the anatomy of the eye. How is LASIK performed? So first of all, the lens is opened, and then the lens is segmented, and then the cornea is opened, and then the lens is suctioned out because this lens is spoiled, and then they put in an artificial lens. Okay, so because one has got cataract, right? So they remove it out and then they put an artificial lens. So cataract operation is very common and it's very safe to be done nowadays. Light. So white LED light, they make colorful light and it can be created by luminescence conversion. So you have the LED light here, so you have a housing for heat dissipation, and this is the lens so that the light does not reflect back into the layer, and you have the phosphor layer over here. So white light is a mix of red, blue and also green. So the creation of white LED light through luminescence conversion, basically you have the LED chip. So you have blue light is emitted, and then you have a yellow phosphor light which converts the incoming light to red, blue and green. And then the red, blue and green together, they make the white LED. Again, this is one of the Nobel Prize winner. Alright. And the spectrum of the white LED lamp, you can see this is the spectrum. And the suppression of the blue peak results in a warmer light. Okay, we try to suppress this because this gives a hot light, so we try to suppress it. And this shows the brighter with LED. This shows a sequence of light produced over the years from 1930 right until 2020 versus the efficiency. We call it lumen per watts. And since the light bulb, we started with the light bulb. So the light output of different types of lamps have significantly increased. You can see this is an increasing trend. So the most efficient ones are white LED. Okay, you can see the efficiency is very high, and over here in green, all right, over the years it has become the highest compared to sodium vapor lamp, compared to fluorescent lamp. Okay, this is fluorescent lamp. And then you also have the halogen lamp, the fluorescent lamp, lampu Kalimantan, okay, over here. High pressure mercury vapor lamp, the normal light bulb. Okay, you can see how inefficient it is. Okay, so that's why LED is very, very popular now, because it is very, very efficient, bright. Cost is also comparatively low, and it gives out very bright light. So just a few years ago, you could find out almost everything you needed to know about the light of a domestic lamp just by looking at the number of watts. But nowadays, nearby a dozen criteria have to be considered. So you need to look at the power, you need to look at the brightness. We also call it the lumens, which shows how bright the lamp's light is. The color temperature is measured in Kelvin. So the higher the color temperature, the colder or the more blue the light will be. The warm-up time, the time it takes for the lamp to light up, and so many other criterias. Okay, we spoke about this, the intelligent luminaires, LED lights. They can be switched on and off. Not only can they be used for Li-Fi, they can also be used for automated switching off. So hundreds of megabytes per second can be transmitted to a mobile optical receiver as an optical function apart from the lighting. So completely without electrosmog or additional cables. So you can use it in museums, in buses, aircraft cabins, and also in trade fair stands. So luminaire, Li-Fi. Okay, this is for Li-Fi. Laser shows. Laser shows are an impressive way of demonstrating how fascinating photonics can be. So you have the laser projector. Two extremely fast-moving computer-controlled mirrors draw the laser image. This bright and high contrast, it is focused at a distance, and then you have a water canvas. The laser projections can be made on a very large screen in any shape or form. And then you can have emission of bright colors, brilliant colors. So only lasers can make colors that are completely saturated. You have green entertainment technology. The energy consumption is low, so therefore it's environmentally friendly. It's also a good entertainment for large crowds because the power is low. You can also have an artificial fog. It makes the laser beam visible. Okay, and this is where the audience are here. And single beams in the sky, this is only possible with explicit. So if someone would like to show a laser beam to the sky, they need to get authorization from aviation safety authorities, because it will interfere with the flights laser systems as well. So they need to get permission to use it on the sky. Traffic. Okay, not so very long ago, we have the AES system implemented in Malaysia. So this is the way AES captures a speeding car. So measuring systems based on the round trip time of emitted and reflected infrared laser beams can calculate the speed of vehicles precisely. Cameras take pictures of the vehicle and the driver if they have committed a traffic offense. So this is a speed camera column unit. You have the camera unit, you have the laser measuring unit. So it's placed at a particular area, and then it emits out light, which is infrared laser light. So over 100 laser beams, 100 times per second. So 100 laser beams every second. There are 100 laser beams going out. 100 times per second. Alright, that's so many lasers. So 100 times 100, 10,000 laser beams in 1 second. So the light impulses emitted from the speed camera column, okay, it is reflected by the passing car and received again by the device. So it sends out the laser, it hits the car, and then it's reflected back and measured by the camera unit. So the measuring distance is 75 meter. And you can have area camera 1 and 2, so you can measure simultaneously several cars, no problem in that. So then you can capture it in a camera. You can even capture the image of your car, and then after that you get a summon letter for speeding. Okay, light on and in the car. So again, LED lights, they are intelligent LED lights, camera based assistance systems, and information displays ensure a greater security in all driving situations. So you have LED lights in the interior lighting as a reading light, rear light, and then you have dynamic LED indicator, rear view mirror camera, rear view camera. All this is using lasers and detectors. Okay, and in the exterior or the interior, you have rain sensor, light sensor, camera for traffic sign recognition. You have a front camera, thermal imaging camera, dynamic LED indicator, and adaptive LED headlight. So the LED is used a lot in cars. Okay, you also have infotainment display, driver information display. All this is using a combination of LED lights and also detectors. Car headlights. So seeing further ahead, the combination of LED and laser light sources enables an optimum for roadway illumination in every traffic situation. So when a car is moving, if it just needs to see a short distance in the dark, so an LED headlight can be used. Maybe there are street lights, so you don't need so much of light. So the intelligent illumination to prevent glaring for oncoming traffic. And then you can increase the illumination using a LED high beam, so large scale illumination of the traffic situation. And for a very pitch dark area, you cannot see anything, there is no traffic lights, and there's no lamps at the side of the road, so you can use a very high laser beam, wide illumination for an optimal vision. Okay, so this shows the laser high beams. Basically, you have a deflection mirror, beam combiner, 3 blue laser diodes, and also a parabolic mirror to emit out the light. Airport lighting. Millions of new LED lamps lower the operation and maintenance cost of airports around the globe. So LED versus halogen, these are two types of light. You can see the LED is in bluish green, and halogen in yellow. So in terms of hours of shelf life, 60,000 hours for LED, and halogen lamp is only 2,500 hours. And the typical connected load per lamp, so the load in a LED is only 18 watts, versus for a halogen lamp the load is 65 watts. So very high consumption of power. And you can see in the runway so many different LEDs are needed for different reasons, so that the flight can take off and also it can touch down safely at the runway. Photovoltaics or solar cell. So solar cells, it can transform sunlight directly into electricity. So an efficiency of around 45% has already been achieved under laboratory conditions. In commercial use, efficiency has to be weighed against acquisition cost. In terms, so there are basically three types of solar cells. We call it the monocrystalline silicon cells, you have polycrystalline silicon cells, and you have thin film cells. So the global market share, the red color is the monocrystalline, is about 36%. The dark green is the polycrystalline solar cell, and finally the thin solar cell is about 10%. So monocrystalline silicon cell is cut out from a round silicon crystal. The missing corners of the squares, okay, is missing. They are characteristics. This form is created because the round cross section of the raw material is exploited in the best possible way. Okay, so because the wafer is round, so therefore we do not want to waste this region, so that's why it's in this shape. And polycrystalline silicon cells, it features a characteristic texture that comes from crystal borders that are very close together. Okay, so it's different from the monocrystalline because this is from a single wafer. So this is maybe from a multiple wafers. Thin film cells consist of amorphous silicon and other material compounds. They can be vapor deposited onto carrier materials, even onto flexible, so bendable. It's like plastic. All right. And in terms of efficiency, monocrystalline solar cells is about 20%, and this is the acquisition cost. It's a bit expensive. Polycrystalline, the efficiency is 16%, slightly cheaper than monocrystalline solar cells. And last but not least, thin layer, or we call it flexible solar cells, the efficiency is 13% for copper indium diselenide, CIS, and for amorphous silicon is 8%. So it's very much cheaper compared to monocrystalline and polycrystalline solar cells. Solar energy, it has the potential to satisfy the world's rising appetite for electricity without polluting the environment. What total size of solar power plants would be needed to run the United States on solar electricity? So the US electricity consumption per year is 4,093 terawatt hours. This is in 2014. And the area of solar cells needed to supply this energy is 12,800 kilometers squared, which is equivalent to the land area of the US state of Connecticut. This is how many solar cells are needed to supply this amount of electricity consumption. And in terms of production comparison, the world photovoltaic energy per year is 180 terawatt hours. Nuclear energy, it can produce electricity volume of 20 nuclear power stations. So 100, this is the world photovoltaic energy, so it's equivalent to 20 nuclear power station. And in terms of crude oil, it is equivalent to 42 million tons of petroleum, and this is equivalent to 140 oil tankers with a capacity of 300,000 GRT each. Who are the top producers of solar energy? So this is in 2014. Now it may be different. So the highest is Germany, Italy, and also Belgium. Environment. Okay. So photonics is also used for optical measurements in citizen projects. So for example, smartphones with attached mini spectrometers, they make it possible to map current environmental data of entire countries with the help of thousands of citizens. So basically you have a smartphone with a mini spectrometer. So the smartphone has got a laser and also a detector. So the laser You can characterize the laser based on its polarization, its spectrum, and also angle. And so it can capture several measured values, and it enables the calculation of fine dust particle values. So you have so much of fine dust particles, all right, traveling around in the sky. So using the smartphone, this information is captured, and this information can be sent together with the GPS location of this area. So you can get information about the amount of dust particles, the size of the dust particles, and also the structure of the dust particles. So these information are sent to central data evaluation concerning the amount, the particle size, and the composition, and then it's mapped accurately in time and location. For example, this is in Netherlands. In terms of pollution, the area in yellow is very strong pollution, and the one in lighter green is very low pollution. So this, you can do a mapping based on this smartphone data. You map it out to the area because you also have a GPS location. Okay. Forest fire surveillance. Automated optical sensor systems monitor large forest areas day and night for us. So for example, you have the surveillance of the Teltow-Fleming County. This is in Berlin, Germany. So the area is 55 kilometers and 92 kilometers. It covers 310,000 hectares. So you have 10 systems in this area. So this is the area being monitored. So basically you have the optical sensor system. So you have two types of sensor system. One is for daytime and one is for nighttime. So it registers smoke development automatically in the visible and infrared spectral range. So the camera turns itself in stages on its own axis over 6 minutes. So it rotates and it captures images and also detects the presence of smoke. So the moment, this is the angle of vision, 15 kilometers and 60 degrees range. And once smoke is detected, the Forest Fire Alarm Control Center receives the data and the image if a fire is detected. So lasers and detectors are also used for forest fire surveillance to check whether there's fire in a big forest. Optical sorting. Efficient sorting facilities are used to recover many materials in their raw form from heaps of domestic waste. So together with fast image processing software, multispectral cameras capture within a split second what should be placed in which raw material container. So you have different types of material with different shapes and different colors, and so they are all moving in a conveyor belt. Okay. And you want this material to be separated by different types of polymer. Okay, you have PE, PET, PP, and so forth. And what happens here is you have a multispectral camera. Okay, and this multispectral camera will detect what kind of material is passing through, and based on the information collected, so either it's a paper or a cardboard, plastic containers, or its impurities, based on the image collected back, it will be sent to the correct bin. So these are all the large bottles, these are all the smaller bottles, and these are the impurities and so forth. So based on the image captured by a laser and also a camera, the separation can occur automatically. Research and so I've already gone through this in my earlier slides. So it just shows photonics as an industry sector. So this is a bit outdated actually. So invention of laser 1960, and it has come a long way that now we have this Photonics 21 roadmap. We also have a public-private partnership between European Commission and also European photonics industry. Photonics around the globe, US and Canada, Europe, Taiwan, China, South Korea, and also Japan. And you can see that the market segments in all the different types of areas, we've also covered this earlier. So who are the Nobel laureates? So we spoke about laser and maser. Okay, this was by Towns, Besov, and also Pokarov in way back in 1960s. And then we move on to the most recent. This is for super resolved fluorescence microscopy. Okay, blue LEDs, I talked about this earlier. So it doesn't capture the 2020 Nobel laureate for the ultra high pulse laser. Okay, so 2018, that Nobel laureate was in 2018. So other Nobel laureates, this is for quantum optics, laser cooling and frequency standards, CCD sensors, which are used in smartphones. Okay, high precision laser spectroscopy, creation of Bose-Einstein condensate with laser cooling, communication via glass fiber, quantum optics, fundamental developments in laser diode, coding and capturing of atoms with laser beams, the electron microscope, the laser spectroscopy, holography, and also optical pumping. All right, so hopefully one day we can see Malaysia here for the for one of the laureate winner. Photonics countries. So the highest density of photonics professionals are found in Europe and East Asia. And photonics schools, there are many photonics schools around the world. For us, the nearest may be in Wuhan. So, but I don't think anyone wants to go to Wuhan now because of the pandemic. And we also have in Sydney and also in Kochi in India. Okay, so number of photonics professionals. Okay, so you can see it's very highly concentrated here, which is in Copenhagen. Okay, economic impact. So so this is a bit outdated. I've shown you the earlier version of economic impact in my first few slides. Okay, what does a photonics enthusiast do? Okay, so an enthusiasm for photonics can also be implemented in the leisure sector. So in a daytime, this photonics enthusiast has a helmet camera. He also has a sports spectacles with correcting curved glass, a rucksack with solar panels, so you have light converted into electricity. You have an activity tracker with an optical sensor. And then at night, he has a rear light projection. He has a wheel spoke lighting, high visibility jacket. He also has a grid projection to detect potholes and obstacles. So both for daytime and also nighttime vision. Okay, so these are how photonics is applied to maybe a bicycle rider. What are the negative impacts, not only of photonics, also all kinds of technology? What are the negative impacts? So the reason I'm putting this in, because some of you are from the social sciences, so maybe you can take up some study to look at these negative impacts and how can we come out with policies to counter this kind of negative impacts. Okay. So technology is actually both good and bad, but what are some of the negative impacts? You can have isolation, obesity, depression, poor sleep habits, pollution, increase in cyberbullying. This is becoming very famous now. Lack of privacy, higher level of deceit, warped sense of reality. Technology can also cause a lot of stress. You can also have a carpal tunnel syndrome. Your fingers become jammed. Lack of social boundaries, lack of sexual boundaries, lack of social bonds. People like to communicate online rather than face to face. Okay, constant distraction, neck and head pain, shortened attention span, and also addiction. Okay, else than that, there is also a lack of empathy, more violence, higher energy consumption, developmental issues in children, neurosis, and also loss of hearing and eyesight. Okay, so those of you who are from the social sciences, you can think about how to come out with policies or how to come out with different types of programs to counter for this negative impact of technology. Okay, so the list of resources that you can go through to get more information about photonics. And in summary, photonics technology has much to offer our society in many different areas. It is one of the breakthrough technology in the area of IoT, big data, and also IR 4.0. So many different areas use photonics technology such as production technology, data transfer, image capture and display, medical technology, and so forth. But the negative impacts of technology must be addressed so that there is a balance of the benefits. Thank you so much for listening, and if you have any questions about photonics or about the slides or about the lecture, feel free to email me at susie@ukm.edu.my. Thank you very much.